give a talk direct in live from my bedroom. This is the worst destination I've ever gone in conference, and believe me, that was not an easy task to be the worst. So thank you, Alice, for the invitation. Okay, today I am going to explain to you why class groups are essential in your lives. So I think right now, for the moment, you're just thinking, come on, class groups for real? I'm not sure that they are that essential. And my goal is that at the end of the talk, your mind change and okay, maybe class groups, they are not that bad that I thought. The first question I want to answer is why do we study class groups? And the first answer is a picture. I hope that everyone here recognizes him. He is the man from number theory, Carl Friedrich Gauss. Yes. The first answer is because Gauss did. He studied class group, and it's a bit more complicated than that because he studied them before they were invented. Yes, Gauss style. The second reason is that class groups are everywhere. Yes, really everywhere, because I will talk about class groups in number fields that are the basic one. But actually, if you look at some algebraic curves, then you get divisors class group, and there are just class groups postponed to in the case of algebraic curves. I don't know if someone is going to talk about that during this summer school, but if you're looking at some Picard groups over abelian varieties, it's just a fancy word to explain that they are just computing class groups over abelian varieties. So actually, class groups are everywhere, but sometimes they have other names just to be more fancy. So if you find someone at a conference that is explaining to you that he's computing class groups, stop him and just say, calm down, you're just doing class group computations. The third point is that it's a beautiful mathematical challenge, of course. Class groups is something easy to define. It's something easy to understand, but it's something hard to compute. This is not normal. When you get a mathematical structure that everyone can define and understand, then it must be easy to compute, but it's not the case for class groups. So we need to explain why is it so complicated, why the definition is easy to understand. And in addition, it's something that you can do at any time. For instance, Saturday night, you don't know what to do, just take at random a number field and then you can try to compute the class group. This is a possibility. You can also compute several class groups and then go to the Wikipedia page of cyclotomic fields and find out that there is a mistake on the Wikipedia page and correct it. This can be a great achievement during your PhD. And the third possibility is there exists a table of class groups. Because, for instance, in the quadratic case, there are a finite number of fields with a given class group, and you can compute them all to put them in a table so that later people will just look at the table and get the results they want. I have done that working on a completely different subject. I was computing genus 2 curves with Jacobian, whose Jacobian splits into the square of an elliptic curve. So this is something not related with class group at all. And in the end, during the progression, we found that the elliptic curve must have complex multiplication by a quadratic order whose class group must be of exponent 2. So at this point, we just check what are the class groups of exponent 2. We found them all. There is 65 of them, if I remember well. And we just list them and try everyone, and we get our results. So class group can also be a tool for some other aspects of number theory. I'm pretty convinced that if you work on isogeny stuff, then you have already heard about class group action or something like that. The fourth point is, yes, it's a finite group. And if you're interested in cryptology, then you know if you have a finite group, then there exists a crypto system. It's direct. However, this crypto system may be weak. Sometimes the security is not there because the operations are easy to do in both ways. So it's not interesting in practice. Maybe it's not interesting because it's inefficient. Because yeah, in cryptography, you want something finite, you want something hard, and you also want that easy computation are done in a reasonable time. So if the classic operations are done in large time, then it's not useful for crypto, because if you need minutes to encrypt a message, it's not interesting. But sometimes just, even if it's inefficient or even if it's weak, maybe you can find an attack in this crypto system and just take it and make it on and do it on another group. And then you, thanks to this group, you find an attack for another crypto system because it was easier to find on this group, and after that you just put it on another one. And last but not least, it makes use of trendy structures, because during this talk I will talk about lattices, I will talk about analytic number theory, that can be L function appearing or Dedekind zeta function. So it's not only class group, but also a lot of number theory. Okay, now we know why we are studying them. I will tell you the story about class groups and where to find them. I would like to thank one of my high school students who did the pictures for me. Thank you, Alexia. And so here is the story I want to tell you. So where to find them? The first thing is that we found class groups in number fields. What is a number field? It's a finite degree extension of the field of the rationals. And thanks to the primitive element theorem, we know that there exists a polynomial T monic such that the field is isomorphic to the set of rational polynomials, to the quotient of the rational polynomials by the ideal generated by this polynomial T. Such a T is called the defining polynomial, and there exist infinitely many of them. Yeah, I will denote by OK the ring of integers. I'm not going to use it a lot during the presentation, but I want to spend a bit of time about the way to represent elements. There are plenty of them, but I want to explain two of them. The first one, I think it's the easiest one and the most common, the most algebraic too. It's just the minimal polynomial. You have an element, you take the minimal polynomial, and you get a polynomial mod T. This is very algebraic. If you're more interested in some stuff with precision needed, then you get the conjugates. For every element, you have n conjugates, where n is the degree extension of the field. So we get a vector of n complex coordinates. And yes, it's very easy to derive a vector of n real coordinates. So here we have the problem of precision, but sometimes it's useful to get a vector than a polynomial. Oh yes, there is still structures I need to define in number fields, because so yeah, we all know that what is an ideal is just a submodule of the ring of integers, and all the ideals, it's a group. We have a group. In this group, we have the subgroup of all the principal ideals that are ideals generated by only one element. This subgroup is normal in the group of ideals, so that you can take the quotient, and the quotient is finite, and it's the class group. So this is the object we are going to deal with during 1 hour. So it's really something easy to define. I think ideal, we have all seen that during before the PhD, before starting our PhD. So ideals, okay, principal ideals, okay, I take the quotient, okay, it's a class group, okay, well defined. I have understood the so yeah, here is the definition of the class group. And of course, if you're fond of that, there is this exact sequence. So we have the set of principal ideals, the set, the subgroup, the group of ideals, and then the class group. Another structure I don't want to talk a lot, but that is mandatory a bit. It's a group of units. This time, this group is not finite, but it's finitely generated. So we can look for a set of generators, which will be finite by definition, and they are called the fundamental units. Yeah, I don't want to talk a lot about that because it's a bit more complicated and not very useful, but they will appear again in some part later in the talk. And you have a second exact sequence. So the units, the field, the non-zero element of the field, and the principal ideal. And if you really like exact sequences, you see that you have both sequences with the subgroup of principal ideals appearing in both of them. And at this point, you can say, oh, maybe you can combine them and get a two-dimensional diagram. Yes, it exists. This diagram is given like that in Cohen's Bible. So he didn't explain all the notation called. He just wanted to show that it was possible. So the first column is about units. The third line is about class group. And I just can say here we have something about S units. And the second line is about ideal class group, not ideal, but ideal. So that's the only thing I want to say. A bit more about number fields. Of course, there are different size, but yeah, different number fields, and I want to give a size to them. This is done by computing the discriminant of the number field. The definition of the discriminant is the square of the discriminant of the matrix constructed thanks to the embeddings of the integral bases. Okay, not really clear, but we know that if we have a defining polynomial, then you have this expression that comes up. It's not an equality, that's a problem, but you see that the discriminant, so the size of the number field, depends of the extension degree on the exponent and depends on the size of the coefficient of the defining polynomial linearly. So two dependencies, because two kind of variables, and one is linear while the other one is exponential. Of course, I will use this size, the discriminant, to give the complexities of the algorithms. And if you are not really familiar with complexities, I will just give really brief outline. you say that the complexity is polynomial when it's linear in, well, not linear, but polynomial, of course, in the size of the discriminant. So when you have that many operations, you say it's exponential when you have that many operations. And the question is what happened between the two? Because most of the algorithms have polynomial or exponential complexities, but we see that there is something between them. It's called sub-exponential complexities, and we have a notation for that, the function L. So one more time, this time we have two variables. Here we get the C that already appear in the polynomial and exponential. That is not really important. The important one is alpha, and we see that alpha is on the term with log, while 1 minus alpha is the term of log. So what does it mean? It means that when alpha equals 0, we have something that is polynomial. The complexity is polynomial. When alpha equals 1, we have something that is exponential. Alpha between 0 and 1, you get something sub-exponential. So what we want to do is to get an alpha as small as possible. Here is a brief history of class group computation. There are not so many papers about that. So as I said, the very first one to work on class group computation was Gauss at the beginning of the 19th century. But it was before class groups were defined, because ideals were not defined yet. But actually, he works on equivalence classes of quadratic forms. And this is exactly the same thing as working on the class group of a quadratic number field. So actually, he did class group computation, but without the objects of class group. In the end of the 60s, Shanks gave an algorithm for class group computation in exponential complexity. We have to wait almost the 90s, so 30 years ago, to get the first sub-exponential algorithm. The first one is from Hafner and Mark Curley for imaginary quadratic number fields, because they're the easiest one. And they get a sub-exponential algorithm in L of 1/2. 1 year later, this algorithm was extended to all number field with the assumption that the degree is fixed. So now the degree can be larger than 2, but it has to be fixed. It cannot tend to infinity. And it gets the same complexity in L of 1/2. More recently, or less and less recent, yes. So in 2014, Bias and Ficker, they extend the results of Bowman, allowing the extension degree 2 tends to infinity. So of course, with that that new condition, the constant in the L notation is larger, so they get something in L of 2/3 in the general case. But they managed to find that, yes, actually, if the extension degree is not that high, then we can get something in L of 1/2. They also give a different algorithm when the number field is defined by a good polynomial, where the complexity is between 1/3 and 1/2. I think we have the first question in the audience, so yes.
Thanks, Alex. What a beautiful story. I'm now so enthusiastic about class groups. However, I still don't know how to find one. Could you tell us a bit more on that topic, please?
Okay, so very good question. How could we compute class groups? Yes, that's a good question. I don't know if I have slides on that. Let's see what happens next. Oh, I think this talk is going to be legendary. So thank you again for the picture. And I will give you the information about how I compute class groups. So I don't want to talk about the first algorithm because it was quite different. And of course, the conditional one only works with a good polynomial. So again, it's different. But the three other are based off the same method, that is index calculus method. It has been discovered 1 century ago almost. And at that time, there is not so many consequences for it. But in 1976, with the paper of Diffie-Hellman, where they propose a new way to do cryptography using discrete logarithms, then index calculus method was discovered again. And from that time, it's something really used, and it has been extended to algebraic curves and class group computation and a lot of other things. It's composed of 3 parts. The first one, you have to fix a factor base. The factor base is just a set of small elements you are working with. So instead of working with a lot of elements, you just fix some of them and you take them small, of course. Second, between these small elements, you want to collect some relations. So you want information just in order to solve the problem for these small elements. And every information will give you a linear equation. And once you get sufficiently many linear equations, then you just have to perform some linear algebra, depending on the problem you're trying to solve. And after that, you get the solution of your problem. So this is the main frame for index calculus method. Now, how does it come to the problem for class group computations? So we are working in a number field, and more precisely in the ring of integers. So we have to take small elements. What are they? We take some prime ideals whose norm are below a bound B, and we have to choose B such that it determines the factor base generates the whole class group, just in order to be able to compute the class group. So we just want to get a bound B such that the factor base actually generates the class group. Does such a bound exist? Yes. The first one is a bound from Minkowski that says that every class contains an ideal of norm smaller than this bound. Okay, nice. Well, not that nice, but we have a bound. Problem of this bound is that there is the square root of the discriminant. So this bound is exponential in the degree. No. This bound is exponential in the size of the discriminant. So if you use this bound in an algorithm, then the complexity of your algorithm is necessarily exponential. That's definitely not what you want. So this bound exists, but not useful. Okay, we need to wait 90s and the results of Eric Barr. Under the assumption of extended Riemann hypothesis, he proved that classes of ideals of norm below that bound generate the class group. Okay, this bound is polynomial in the size of the discriminant, so that can be useful for us. And that time we have a bound that is polynomial so that we can get an algorithm that is not polynomial. No, it doesn't work like that. Because if you take this bound precisely, then of course the complexity can be polynomial, but you have a factor base that is really small, and it's very complicated to find some relations between a set of small size. So we will enlarge this set, get something larger, but smaller than exponential, and that's the apparition of sub-exponential L function. So we get something sub-exponential, so larger than polynomial but smaller than exponential, so that with that size, the factor base is large enough to allow computation and relation collection in the factor base. Okay, so it's been almost 20 times I'm talking about relations, but you still don't know what it is. So we have the factor base composed of a finite number of prime ideals, and the factor base generates the class group. So if I take this morphism with the vector in z to the n, I construct the product product. So this is an ideal, and then I take the class of this ideal in the class group. This is a morphism, well, and it's surjective because the factor base generates the class group. Because I have a surjective morphism, then I know that the image, that is the class group, is isomorphic to the quotient of z to the n by the kernel of this morphism. What is the kernel? One vector is in the kernel if the power product is 0 in the class group, so if the power product is a principal ideal. So when I say I want to find a relation, what I want to find is a vector in z to the n such that the power product is a principal ideal. These are exactly the relations I want to collect. Okay, but how can I do that? Here is the idea of the algorithm. So at first, I pick at random an ideal. I take a power product just to ease the computation. Then there is a reduction step to get another ideal. I'm not talking of the reduction right now, but as my slides are very well done, I'm pretty sure that it will happen in the next slide. So for the moment, forget the reduction, and you get another ideal. These two ideals, they're in the same class. That is, ideal A equals ideal B times another ideal that must be principal. So here is the apparition of a principal ideal. Okay, and if the reduced ideal splits over the factor base, then of course the product between A and the inverse of B also splits. Then you get an ideal that splits over the factor base, and that is principal. So it gives the vectors AI minus BI in Z to the N. That is a relation, that is an element of the kernel, so it gives us a relation. And I do that many times to get many relations. What is this reduction now? Okay, ideal reduction, that's not something that sounds really good. We don't heard a lot about ideal reduction, but when you have an ideal, then you can take the embeddings and get a matrix, and to this matrix correspond a lattice. And do you have ever heard about lattice reduction? Yes, this time, yes. So from this ideal, I construct a lattice, and I will reduce the corresponding lattice. The lattice that are constructed thanks to ideal, they have a name, and it's ideal lattices. So when you see in the literature ideal lattices, it's not lattices with some additional property. Yes, it is, but it's not a specific kind of lattices. It's just a lattices coming from an ideal. But of course, there is additional. Well, yeah. Not a good way to explain it, but okay. So now I perform lattice reduction, and there are several kinds of. I don't want to get through the details, but the first algorithm by Burman was to find the shortest vector. This is something that can be done. It costs a lot, but the result is, of course, as short as possible because we get the shortest vector. So the ideal we get in the end, the ideal B, the reduced one, is very small. That that enlarge the probability that it splits. If the norm is smaller, then the probability of splitting over the factor base is larger, of course. The problem is that this algorithm, finding the shortest vector, is exponential in the extension degree. That's why Bowman, in his results, must fix the extension degree. Otherwise, it's no more a sub-exponential algorithm. What Diaz and Ficker did, it's, again, finding a balance between that. They say, okay, I don't want something exponential. So I am not going to find the shortest vector. I will stop when the complexity is sub-exponential. What can I get? I will get a short vector, not the shortest one, but I can get a short vector. For that, they use the BKZ algorithm, so Bloch-Corkin-Zolotarev, that offer a trade-off between the time span and the approximation factor. So the reduced ideal B they get is not as small as the one of Bowman. That's why the probability of splitting is smaller. So they have to make more computation or to enlarge the factor base. That's why the complexity is larger. But now the extension degree can tend to infinity. After that, the linear algebra part. So we have collected sufficiently many relations, and they are all stored in a matrix. And we just want to find the results we are looking for. So this depends on what you are computing. If it's just discrete logarithm problem, or I think algebraic curves is the same, the linear algebra corresponds to solving a system. So this is something well known. Most of the time, the matrix is sparse, so we have efficient algorithm. But for us, it's a bit more complicated because we don't want to solve a system. We want the structure of the class group, and this is given by the Smith normal form of the matrix. So we have to compute this Smith normal form. We have an algorithm in n to the omega plus 1, where omega is your preferred exponent of matrix multiplication. And during the computation, we will compute the Hermite form with a premultiplier, because you will see it's going to be interesting for the following slide. Because yes, I said there is 3 parts in index calculus method, but this is in the general case. But for class group computation, one more time, it's a bit more complicated. Why? Because maybe at this point, what we get is not the class group. What we get is just a candidate. Sometimes it's not the class group. Why? Where is the problem? So I want to be clear. We assume that the factor base generates the class group. So here there cannot be the problem. The problem cannot be here. The factor base is good. Okay, so where is the problem? It happens in the collection of the relation. Maybe we have a lot of relations all in the kernel, but all the relations are in a subset of the kernel. And what we get is not the kernel, but only a subset. So when you take the quotient, you don't take it for the whole kernel, but for something smaller. And then you don't get the class group, but something larger than the class group. And then the class group may be only a quotient of your candidates. Okay, but how can I manage to find the class group? I don't know. I need an approximation of the class number. If I know an approximation of the size of my group, then it's okay. I will check if it's a good one or not. Okay, is there such a formula? Yes, the class number formula. Yes, not quite simple formula, and I have hidden the worst part because here I have got an alert product, so it's just a product, an infinite product that you can approximate using using its ideal of prime ideal of small norm. But this actually this is a good enough approximation of the residue of the dedeking zeta function associated to the number field. So this is the very ugly part of the class number formula, but thanks to Euler products, this can be approximated and computed in polynomial time. After that, we get the roots of unity, number of roots of unity, the square root of the discriminant, and a constant depending on the number of real complex conjugates. So this can be approximated in polynomial time. And this is an estimation of the class number times the regulator. So there is still something I don't know in this formula. What is the regulator? It's almost the same thing as the class number, but in the case of group of units. Remember, I have talked about units at the very first part. So it's something finitely generated. So if I have units, I can find some candidates for fundamental units. And then this is an hyperplane in an r-dimensional vector space. So you can embed it with a logarithmic function in addition. And then you get, because it's an hyperplane, you need to delete one line, and then you have a matrix, a square matrix. You can take the determinant with a sufficient precision, then you get the regulator. It's complicated. I don't want to go into details, but it's possible if you know units to get a candidate for the regulator. And one more time is just a candidate, but I have a candidate and I can test if this equality is approximately verified or not. And what is important is that both the class number and the regulator are calculating decreasingly. If my candidate is not the class number, then what I get, its cardinality, it's an integral multiple of the real class number. So if it's not the good one, it's 2 times or 3 times the good one. And it's exactly the same for the regulator. So that if this equality is verified, it cannot be a balance between both of them. No, the two, the class number and the regulator, must be the good ones. And yes, now I just need to say where we can find units. I've already said that units are given because there are elements in the kernel of the matrix relation, the relation matrix, the matrix where all the relations are. You compute elements in that kernel and you get units so that you can get a candidate for the regulator. This part is not the easiest one, but algorithms exist and it's sufficient. Here is the state of the art about class group computations. So in abscissa, we get the relative size of the extension degree. So here we have, on the left, we get a number field of small dimension 2, for instance. And on the other side, we get large degree, so cyclotomic fields. And if I translate the results of Bias-Ficker in that diagram, then I get something generally in L of 2/3, but most of the time when the extension degree is not that large, L of 1/2. This representation is not fair for this paper because the classification, the proof that we can get such a diagram comes later. So it's unfair to give a picture of what they get because it's used a classification that didn't know. And here we get something in the small degree case where we have a conditional improvement if we get a small defining polynomial. Okay, during my PhD, I just refined the second constant, and because of the classification, we were able to get something linear for the complexity that is most common, and just a small refinement in very large degree case. Okay, now we have time, yes, to talk a bit about the conditional improvement when there is a good defining polynomial. First question, what is a good polynomial? We know that there exists infinitely many defining polynomials, that the degree is fixed, so we can just play with the coefficients. And of course, we want them as small as possible. So we define the height of the polynomial, that is the maximal coefficient, and that is the one we want to minimize. And yes, I recall this formula. So this is an inequation about the height of the defining polynomial. We have a lower bound, and we do not know if this lower bound is tight or not. There is no result for the moment, at least, saying that yes, I can always find a polynomial t such that this inequality is as close as possible of an equality. Why minimizing the height? If we have a good defining polynomial, we can get rid of lattice reduction. We just have to look at small algebraic integers that are integers whose minimal polynomial is small too. So we get a bound, we take a bound on the degree, we take a bound on the coefficients, and then I know that the norm of this small integer is bounded by, yes, so the extension degree and the height of the polynomials. So if the defining polynomial has a small height, then the norm of all the elements will be small. And if the norm is small, then the probability of splitting is large, of course. How can we find such a small polynomial? This is just lattice reduction, but a tricky one, because if you perform a classic lattice reduction, then you will minimize the L2 norm, and when you minimize the L2 norm, then you see that all the coordinates of your vector are of the same magnitude. So if they are all about, say, a constant c, then the last coefficient of your polynomial, yes, will be c to the n, if n is the degree of the field. That's not what we want. We want the contrary. We want all the coefficients of the polynomial to be about the same magnitude. So we don't want to reduce the lattice thanks to the L2 norm. What we do is, what we prefer is to find one dominant coordinate and all the other very small. I will give you an example. This is a very nice polynomial. It was my best friend during my PhD. Look at the conjugates. They are all between -1 and 1, except the last one, that is almost the larger coefficient of the polynomial. And here we see that polynomial has small coefficient. If I look for the shortest vector in the sense of L2 norm in the lattice, then I get this vector. Okay, the L2 norm is shorter, way, okay. But look at the polynomial it gives me. I don't want to perform computation of resultants using this polynomial. It's insane. So that's why we need something to find a small defining polynomial in order to reduce the complexities, and also in practice. At the beginning of my PhD, when I gave this polynomial to Magma to compute the class group, he said, okay, I take your polynomial, I first reduce it, and the reduction gives this polynomial. And after that, after this initial reduction, it only works with this big and ugly polynomial instead of the beautiful one I gave it to him. So now I think it's corrected, but it was a problem. Once again, an outline of the state of the art. So this was the conditional improvement thanks to our algorithm for finding a small defining polynomial. This is no more a special case because we can always find a small polynomial. So this is now the general case if the extension degree is small. Otherwise, it costs too much to find a small defining polynomial. So we prefer using lattice reduction. Okay, so it didn't work. It didn't work when the degree is large. But if the number field is given by a good defining polynomial, I don't have to look for it. So it costs nothing. I just have to read it. And in that case, I can do the same algorithm without doing the reduction because it's already done. And then I can find something that is between L of 1/3 and L of 3/5 in the worst case. This is the current state of the art for class group computation, I think. I think it's time for a second question.
My question is, what can we say to people who are bullying us because they think there is no application for this kind of math?
Yeah. So a lot of people say there is no application of class group computation in the real world. So to all these people, I want to tell us the story of class groups and cryptology. Yes, there is a link between these two things. Thank you again for the illustration. Now you will see one of my illustration, and it's quite different. For those who are not familiar with cryptography, a very, very light explanation. Bob has a secret, so it's his private key. And from his private key, he is about to derive a public key that he can share to all over the world. Yeah? Everyone can use the public key to encrypt a message, but only Bob can decrypt this message thanks to the private key. This kind of cryptography is based on mathematical problems that are called one-way function. That is, it's easy in one direction, and it's hard in the other one. For instance, multiplication, it's easy. Factorization, it's hard. Another possibility is to use the principal ideal problem. So it consists in finding a generator of an ideal, assuming such a generator exists, so assuming it is principal. Of course, this cannot have application in cryptology, because in cryptology we want efficiency, so we want everything involved small. Okay, no problem. There is his little brother, the short principal ideal problem, that consists in finding a short generator, assuming such a short generator exists. This is the base of several crypto systems, yes. Smart and Workout Turan presented one at PKC 2010. There is Garrett Gantry and Alevi multilinear maps. And the solution is given in two steps. The first one is to find one generator, not necessarily small. And the second one is, given one generator, find a small one. The second part is well studied. It has been given by Campbell, Groves, and Shepard, and then proved by Kramer, Duca, Peikert, and Wegeff. So extended to all prime power cyclotomic fields, so no problem. The only remaining question is solving the PIP. This has been done also in the quantum settings, and in quantum setting, I think it's polynomial now. Not sure. Yes, it's polynomial. Here is the scheme of smart and dark-out events. So you take your preferred cyclotomic field, big enough to answer security. Then you take a generator with small coefficients, so between these two bounds. And of course, you want to get the norm to be prime, otherwise the problem splits and it's unsecure. Then the private key is the generator, and the public key is any other way to give the ideal. I choose the Hermite form, but you can give it with a two-element basis, an integral basis, as you wish. Complexity. No, the goal is to recover the private key from the public key, of course. Algorithm in 4 parts. The first one is not interesting at all because it's just dividing the dimension by 2. Then we get the descent, more interesting, something really similar to class group computation. And after that, just get the small generator for a larger one. I will give the complexity using the L notation. So yes, the first part is just halving the dimension. It's based on the Gentry-Seidler algorithm, so it's not really interesting in theory, but in practice, using a lattice of dimension 256, it's much better than to use 512. So this is more useful in practice than in theory. After that, you have the descent. So you get the ideal, you are looking at the generator, and you perform a first reduction. You get something whose norm is bounded by L of 3/2, and you know that with a probability in L of 1/2, this is L of 1 smooth. L of 1 smooth is quite big, again, still. But you can do that several times. And the next step, the norm you get is L of 5/4. So this is L of 3/4 smooth with probability L of 1/2. And you see that the norm of all the ideals involved shrinks at each step. And if you do that again, 9/8, so this is L of 5/8 smooth with probability L of 1/2, and you do that, in at the end, what you get is something that is L of 1/2 smooth. So at the beginning I have a large ideal, and at the end I have a lot of ideals, but all of norms smaller than L of 1/2. What can I do with these ideals? Do exactly the same thing as we did for class group computation, index calculus method. So we put them all in the factor base, and we collect relation between them. Here we are in the case of cyclotomic fields. So there exists a good defining polynomial so that we can look for ideals generated by these small elements, and we can construct the matrix in that way. And then at this moment, you can compute the Smith normal form if you want the structure of the class group, but that's not what we want. We want to solve the problem for all we want to find a generator for all these ideals. So we just give a solution of the system, and this solution of the system will give us a generator for the product of all the ideals involved in the very last step of the descent. But as we keep in memory all the intermediate calculus for the descent, we can backtrack it, and then we get a generator for the initial alleele, and the problem is solved. So we are happy, and I'm happy too. This is the end of my talk, so I would like to thank you for your attention. Here is the Instagram of the illustrator of all my pictures, and if you have questions, I will be happy to answer them.